Hello, ladies and gentlemen. My name is Chiravachradej. Welcome back to our courses. This will be the first lecture in our second half of the course. Today we'll talk about stress transformation and continue it up to the concept of how we can use Mohr circle to calculate this stress transformation. The technique will be the same as the one that we employ to use in the orientation of the area moment of inertia. Okay, but this time we apply the same technique to calculate the stress transformation. Okay, let's carry on. Okay, and we see how it apply later. Okay, when we're gonna go there, we talk about background knowledge first, and then we talk about the stress transformation. And then we'll talk about the general concept of the stress transformation, the general, and then we'll talk about the formulation. Once we achieve that the basic formulas, then we will actually try to achieve the maximum and the minimum value of the normal stresses that we call maximum and minimum principal stresses. And we also will find the maximum shear as well, which we call maximum in plane shear stresses. And of course, then we carry on with that formula and see how we can apply the technique of Mohr, that we call the Mohr circle, into solving the problem instead of using equations. Now, the background knowledge, apparently in this state, we have to use a lot of circles and triangles, so basic knowledge of trigonometry will be needed. Then we will need the general understanding of the normal stresses, of course, and the shear stresses. Now, this Mohr circle, this stress transformation, is the interaction between the normal stress that we actually know so far in the name of axial stresses, and also it will interact with shear stresses. This is the general view of how the three-dimensional stress is applied onto any single element in the body that accepting to the force. Of course, we can see the components of the shear stresses and the the normal stresses. The normal stresses, which is actually the concept of the axial, is that it will be 90 degrees to the surface that is acting. Notice on that surface, then that one is 90 degrees. So sigma, in this case, is the normal stress, sigma y on that one. That one then, according to that surface, is 90 degrees. Whereas the shear stress will be the one that's sliding the surface, again, the same concept there. Okay? But in this case, they have different directional for shear stresses as well. Now, of course, the face behind here will be exact copy of that. The face behind here, the area behind here will be that opposite direction, will be the same, but opposite direction, of course. Okay. Now, when we talk about this stress transformation, we are talking about a general concept that we simplify into two-dimensional, which means we will have only this one. Notice that this one here, the plane stress state, meaning it's only on a plane. The stress happening on the plane. Okay, meaning there's no third direction. It's only vertical and horizontal in this case, so it's a plane. Okay. Notice that these two here, this one will be associated with the axial stress that we know. That one is the transverse shear stress and longitudinal shear stress, of course, and that is normal on that part. On the top-down part. Okay, so we actually reduce the problem into the plane stress rate, meaning simplify actually. So if we look at maybe the front view, we should see that picture there. Okay, sigma x, the normal stress in the x direction, left, right, then normal stress in the y direction, up, down, and then of course the transverse shear and longitudinal shear per se. Notice that this alignment is in fact xy coordinate, as we actually assume in general with the directional of the member. For example, beam will be x, y, right? Beam x is the length of the beam, y is the shear. If the column is y and then the shear in the x, right? Now, apparently we align it that way because it's easy for us to see the picture. It's easier for our perception. But when the material actually taking the force, it doesn't actually take the force separate, x and y. It takes them together. Meaning, if we look at the same element, notice my wording carefully. It is the same element, but from the different perspective. Maybe from a different axis of x and y, which we're going to call x prime, y prime, that way. Okay? Of course, still, the stress when we take it out is still 90 sigma. The normal stress is still 90 degrees to the cross section, 90 degrees to the area it is acting on, and the shear stress is still sliding it. Okay, so that will become the picture on how we should draw it. And of course, the xy coordinate, but the xy coordinate change into x prime, y prime coordinate. However, since it is the same element, as I said, we just change the way we look at it. We change the way we cut it. Meaning the force system on the left hand side and on the right hand side must be equivalent. When you combine everything up, it should be the same. Force y and the whole system become equivalent. Superposition, right? So, how do we actually relate these two systems, these two perspectives? Then first, let's compare the angle first. Okay, let's say that we're going to turn, for the first study, we're going to turn this element, compare this element, the normal xy and the x prime, y prime, with the different angle of theta. Okay, as I show down there. Then we'll cut along this y prime axis. We'll cut that element along that y prime axis, and therefore we cut it down here, meaning that angle is theta. Opposite angle here, theta as well. Once we cut it, we're going to draw that small triangle here. Okay, that triangle here. There we are. And we see that. Right? And I said, if it along the x prime, y prime, then the stress will become sigma x prime and tau x prime, y prime. The rest is acting on the same. Now, notice that the symbol here hasn't been changed. The reason being, when you cut the element, these are the stresses which actually distributed all over the area. Therefore, the magnitude doesn't change, it just covers a smaller area down here, that's all. Okay? Now, this is the stress pattern, the stress symbol, meaning we cannot use sigma fx, sigma fy yet unless we know the area is acting on. So let's discuss about the area first. That is the axis, okay? The comparison. Now, if this is the element, this is actually the front view. The area we're talking about the one that the stress is acting on, meaning that area, and that area, okay? Now, for the point of comparison, that is 90 degree, that is theta, 90 degree, theta, right? That's the same picture. Now, let's say that this length here is L, capital L here, and the depth is dz. So if you look at this view, you will see a rectangle with the area of L times dz, right? So that, let's call that dA. dA is only on that one, okay? Not this triangle, this rectangle when you look at this view. How about that one then? If that length is L, then from the triangle, that length will be L cosine theta, right? If that is L cosine theta, then in respect that is L cosine theta. The depth is still, is the whole wedge, the same wedge. Therefore, the depth is still dz. That depth is dz. Meaning that area, when you look into it, it is L cosine dz. Now, if you look at L dz is what we call dA. So L dz is dA. L cosine theta dz become then dA cosine theta. The same argument also apply at the bottom there. Okay? Then that length will be L sine theta, right there. And then of course the area become dA sine theta. Okay. Now, these two stresses at the bottom act on the area dA sine theta. On the left hand side, that's sigma x, and that's tau xy acting on the area dA cosine theta. And these two stresses, sigma x prime and shear stress tau x prime y prime, acting on that area, which is dA. Okay. So now we know the stresses, or at least their names, and then we know how we use the area. Well, in terms of comparison, anyway, then it's time for us to actually maybe doing the equilibrium. Okay, that is a summarize here of the picture of the stress state on that wedge. That is what we summarize on the area. So next, what we do is we'll start using the sigma fx, sigma fy. The first one I want to do, because we assume, well, we should be able to calculate sigma x, sigma y, and tau x prime y prime by now. So the one that we actually want to know is sigma x prime and tau x prime y prime. So to have only one unknown in our equation, therefore I will actually do sigma fx prime one time and sigma fy prime one time, so that we dealt with one unknown at a time. In sigma fx equal to 0, sigma fx prime is equal to 0. Then we have only sigma x prime as unknown. Okay, so let's talk about the format first. It's going to be many terms in it. So let's talk about format. We'll talk about a force will equal, in this case, the first bracket. Then we'll talk about stress times the area. Then it becomes force, right? And then because sometimes it's not along the axis line, you have to take component into the axis line. So that is, then we have to time the directional components, sine theta, cosine theta, something like that. Okay, so let's see it. Look, that is the whole equation for sigma fx prime. Whoa, right? Don't worry. Let's go one term by one term. The first term come there. It's from sigma x prime, right? It's time dA is already on x prime, so we don't count it. Then the second term, that one there doesn't count because it's 90 degrees, so we ignore it. The second term comes from that sigma x and there. Okay, sigma x, that sigma x is acting on dA cosine theta here, right? And then of course, once you come as a force is on that line, right? On that line, on x line, not on x prime line. So you take the component here, from here to here, then we use cosine theta. Okay, and then the same explanation term by term. That sigma tau xy calculate as a force. Then we end up with the third term, and then move on sigma y tau x, and then of course sigma y and then tau x tau xy. Okay, and each term matches the same thing. Stress times area is the force on its own direction. Then we time the directional sine or cosine. Okay, once we understand this term and know where it comes from, then we move on and actually we dealt with that equations. That the equation that we showed last time, we just move it on the top. By the picture, by the look at it, it can be arranged first. Notice that every single term has dA. Therefore, we can use dA, divide them all, and then the term dA disappears from the equation and we become a little bit shorter. And of course, we put in sine, cosine into the bracket as well, and we arrange into that form. Now, in terms of mathematics, when we have sine times cosine or sine square, cosine square, it's kind of hard to picture what is happening in the graph. I mean in the graph term. So we're going to try to arrange it. Okay? Oh, hang on. Let's explain where it comes from first. It's matched term by term, of course. There we are. Then next we'll start to try to arrange, as I said. Okay? The first thing first, then we notice that there are repeating terms. Okay, so we just move those repeating terms together. Okay, meaning the tau xy term. Okay, so now we reduce it even further. Again, the cosine square, the sine square, or cosine times sine is a little bit hard to imagine the graph. So what we do is we try to expand it into power 1, but use 2 theta instead. And these are the 3 equations we've seen before that can transform cosine square into cosine 2 theta, sine square into the form of cosine 2 theta, and of course sine theta, cosine theta into a form of sine 2 theta. Okay, and once we do that, then the formulation change. To substitute into it, we have that terms, and we run off the space in this page. So we shall move on to the next page. There we have just moved the equation from below up to the top again. Now, once we see these equations, we should realize that maybe we could actually regroup it. Okay. So first, to regroup it, we expand it first. Let's see where it comes from. Okay, and then we rearrange it. How? Here. Right? Those 2 terms form the new first term. Okay, and the second and the fourth term form the second new term, and of course the last term remain exactly how it is. Okay, so basically this equation tells us if we know, which we should be able to calculate from the force system, sigma x, sigma y, and we know how much we're going to, and tau xy, and we want to turn the element, change our perception, we can calculate sigma x prime apparently using the equation. Okay, so we shall mark that as equation 1 for now. Once we've done that, then maybe we change the equation. We go back to the same picture first, using the same format. Okay, then this time we'll go through sigma fy prime. Okay, and again still in equilibrium, so the summation of force must be 0. Using the same format, then we turn out in this set of equations. Okay, again let's go one by one so we don't get lost. Of course, the first one here, sigma x prime, this time doesn't count because it's 90 degrees to y prime. Ignore it. The first term therefore comes from tau x prime y prime, and then sigma x on the left hand side and the tau xy on the left hand side. Okay, the next 2 terms will be sigma y and then tau xy at the bottom. Oh, sorry, one more click. Okay, so now once we match all the forces or the stresses or the caught forces onto the equation, then we move on to the next page. Okay, moving the equation onto the top, the long equation again. This equation, every single term has dA again, so we eliminate dA from the equation because dA is not 0. You can use dA to divide the whole equation, and then leave sigma x prime y, tau x prime y prime on the left hand side, move the other thing onto the right. Now again, we start to regroup them. Now let's see how it goes. Okay, there, one by one. Okay, then of course, using the same set of equation we used last time, we can reduce the sine square and cosine square and sine times cosine into power 1 of sine cosine. Okay, there we are. Now, once we got that form, we again rearrange it. Okay, that the terms where it come from. And then now that one is we expanding it, and now we regroup it. Okay, that one go there, that one go there. Okay, and of course the first term doesn't change, the same. Now we regroup them, completely regroup them, which means we end up with that as equation 2. Well, the reason we changed that so that it match to our equation 1. If we leave it that way, it doesn't match directly to the equation 1. That one is the same form but with minus in front. Okay, that's the reason. So let's summarize what we have so far here. There we are. We actually have calculated, if we know sigma x, sigma y, tau xy, and we know how much we want to turn the element, then we have equation for sigma x prime, tau x prime, y prime. Now, maybe we should do sigma y prime, but apparently something is actually should be noticed here. Something should be noticed here is that if we turn this element, this element 90 degree more, it becomes y prime, right? Therefore, rather than finding y prime, what we do is we just substitute that 90 degree more. That's all. We just turn it 90 degree more. Not one thing though we should notice here, when we turn element, we turn only one theta. It appears in the equation 2 theta. Okay? But the physical of the angle of the physical is only 1 theta. It appears in the equation 2 theta. I have to emphasize it because it will become of importance really soon. Now, when we look at these two equations, one other thing that we should notice that if we do not change the point, if you remain look at the same element, then sigma x, sigma y, tau xy will not change their values. Okay? However, if we keep moving theta, keep changing the way we look at theta, of course this is not constant. Sigma x prime is not a constant, tau x prime, y prime will not be constant. Okay? As an engineer then, if it's not constant, meaning it's possible that we must deal with the maximum value of both sigma x prime and tau x prime, y prime, meaning the maximum of the normal stress and the maximum of the shear stress. Okay, because that is when the structure fail, it fell with that value, those values, the maximum values. So we need to find it, which brings us to the next step. We will start from finding the maximum normal stress first. Now, this maximum normal stress apparently is called by the name of principal stress. So we will keep with the tradition and call it principal stresses. Okay? Definition is the maximum and the minimum normal stresses. Question: why do we need maximum and minimum? I just said that we only need maximum. The answer is, if we look at the equation closely, it is mathematics, meaning it will always think negative is less than positive. We are engineers. We know that it's not true because negative in our sense means it changed direction from the positive. Okay? So the word minimum for this calculation tend to be mathematically minimal, whereas it could be maximum in engineering sense. So we need both value, maximum and minimum. Okay? Now, this is, as I said, this is the normal stress, maximum of the normal stresses. Therefore, this is the equation. Now, if we know the equation, we know what it varies to, or what it varies with, or sometimes they call vary with respect to something. In this case, it's not respect to x or y, it's with respect to theta that we keep rotating. Again, I emphasize it change with, when we change, we rotate element by 1 theta, meaning all these change caused by 1 theta, not 2 theta. We turn it 1 theta, equation appear 2 theta itself. So when we do differentiation, we do not do it with 2 theta. We do it with the real turning 1 theta. Therefore, the maximum will be, as I said, using the function differentiate with theta, d sigma x prime by d theta. And of course, if we differentiate it, then we can distribute it into the term. Now the first term here, a constant, differentiate it, becomes 0. This term here, the first term constant, come outside, and then differentiate the cosine 2 theta. This one is the same. Tau xy constant come out and differentiate the variable term. Okay, and then that is how we end up with the differentiation. Okay. Now, this is just the differentiation. If we want to find max and min happen where the slope is 0. Differentiation gives us the slope. If we want max and min, we find out where that slope becomes 0. In other words, we just set it equal to 0. Okay. Now, once we have it equal to 0, look at that form. Apparently, we should realize this theta here, once we set it equal to 0, when we set the slope equal to 0, this is not any theta. This is theta where we find the maximum and /r minimum value for the normal stresses. Therefore, it is a specific angle, specific theta. In this case, we name it theta p, principal angle. Okay. Now, in that form, we can actually solve theta using the tangent there. And of course, once we find the theta, then we can substitute it back into the equation we already have, sigma x. Then we can actually find out what it is. What is the maximum value or minimum? So, and as I said, sigma p then signifies the orientation of the plane of the maximum and minimum normal stresses, meaning it's the theta where you turn the element and you find the maximum and /r minimum, maximum and /r minimum normal stresses, which we call principal stresses, of course, maximum and minimum intact. However, they kind of feel that maybe we can find it straight away and substitute it back into the equation straight away rather than having to find real application. So what they do is they use triangle. Okay, the tangent of an angle comes from triangle, of course. If we draw a triangle that way, notice the height, tau xy. This is the size of it, and then of course the base, the side of the base is tau sigma x minus sigma y over 2, meaning that term basically. Then of course that angle will be defined by 2 theta. And if we notice now the name changed a little bit, it's no longer just theta p, it becomes theta p1, because we realize once we're talking about this, it means that it has the whole circle, meaning that has another angle as well. But let's remain on the top angle. So if we know two sides of the triangle, this is 90-degree triangle, Pythagoras, then we can calculate that size, the length of that size. Of course, they're both the combination of them both square in the square root. Once we get that, meaning we could actually tell what is sine 2 theta p1 and what is cosine 2 theta p1. Okay, just normal trigonometry. Now, notice that once we have these two terms, because the equation we have is already in the sine 2 theta and cosine 2 theta. This one here is, as I said, is the minimum principal stress, meaning it turns to the other side of the equation of the angle. Okay, it's the opposite of that, evil twin of that, of course, if you want to say it. But then the idea is the same. Okay, that sine can be calculated the same amount, and of course we can work out that sine 2 theta p2 and cosine 2 theta p2 as well. Again, use simple trigonometry. Once we have this expression for sine, cosine, for that one we will be assuming to be maximum principal stress, and that one the angle or the orientation of the minimum principal stress. Okay, the two different, the difference in the angle, if you look at the triangle, it's a straight line. Okay, Therefore, the difference between these two is 180 degrees, meaning the difference between theta is 90 degrees. Meaning, if you set on one axis, don't forget x prime, y prime is also 90 degrees. Meaning when you turn the element up to one line, you get maximum principal stress. The 90 degree line become automatically minimum principal stress. Okay. Now, if we substitute into the equation, this is our equation 1. As I said, we have it in the form of cosine 2 theta and sine 2 theta. Next is we just substitute that into that. Okay. Then we will have this form. Notice what happened in the bottom down here. That term and that term is the same term, meaning it can be used the same, and that term and the same as that term the same as that term. We will take advantage of that. That is the old equation just on the top and then there. Okay. And as I said, at the bottom is the same term, meaning we can just combine the top. If we combine the top, then we should say that it's the same as inside the square root. Okay, it's the same concept as 2 over square root 2 equal to square root 2. It's the same thing here. And then we end up with the last expression. And that is the expression for the maximum principal stress. Of course, when we find the orientation of the maximum principal stress, as we discussed before, we also see the orientation of the minimum principal stress as well. Therefore, the theta P2 signify the minimum. Let's go to find shear stress first. Okay, on the maximum principal plane. Okay, from equation 2, if we substitute the angle that we find for theta P1, then we substitute into that, we have that form. Okay. Notice that it becomes 0. That tau the same tau, that term the same as that term, the divider is the same, minus, plus, then becomes 0. Okay, meaning the shear stress attaching to sigma 1, the shear stress attached to maximum principal stress is 0. Okay, in the minimum principal stress, then we use theta P2 for it. Okay, this is the theta P2 we found before. Okay, that is the equation for sigma x prime. Substitute the angle into it, we have that one. Okay, let's move it on to the top. That term and that term the same, that term and that term the same. It becomes that form. Divider the same, and then of course it be reduced that one. Now we should notice that when we prove for sigma 1 the maximum principal stress, this term here is positive. When it becomes minimum principal stress, it becomes negative. So usually it written in the same equation in this form here. Okay, and use plus minus. Now, if we look at the shear stress attaching to the minimum principal stress, then using the same idea like last time, using equation 2, which actually used to calculate shear stress, substitute into there, and then work out substitution, then you have that form. Again, if you notice, the similarity, one is plus and one is minus, and of course, again, becomes 0. And we could summarize that the principal stress concept is that we can find out theta P or the orientation of the principal stress, maximum and minimum, by this equation. Okay, don't forget there are two angles here. Your calculator gives you only one angle. you are the one who has to know that there must be two angles here. The differences between the two theta P2 and theta P1 difference is 180 degree. Therefore, theta P1 and theta P2 difference is 90 degree. And of course, the maximum principal stress is, and the minimum principal stress can be calculated by that expression, plus and minus. And the shear stress on these two planes are 0. If up to this point you haven't got any break yet, I suggest you have a little break here, at least 5 minutes before continuing. Okay? Because I will do. Okay, I hope you already had your break. But now let me summarize it a little bit. We actually noticed that when we rotate element around, then the normal stress and shear stress changing value. With that change, we recognize the fact that there must be a maximum value, or there could be a maximum value that we have to concern with. So we find out the maximum normal stress, which we call maximum principal stress. And along the process, we also find the minimum as well. And as I said, minimum in terms of mathematics, it means negative is always smaller than positive. In engineering sense, it's not. In engineering sense, negative means just changing direction. So we also need to find the minimum value as well. And therefore, we concern ourselves with maximum and minimum principal stress, as we indicate here. And of course, on this, when we free the sigma 1, the maximum principal stress and the minimum principal stress, the shear stresses are 0 here. Now, of course, if we can find maximum normal stresses, then we should be able to find the maximum shear stresses as well. This one here will be called in-plane shear stress, maximum and minimum, of course. The definition is the maximum and the minimum shear stresses. Okay, that is the equation. Again, I emphasize this equation change with theta. We never change the point we are looking at. It's the same element, the same point. Okay, since it's rotating with theta, and therefore we differentiate it with theta. And with the same argument, we can do the term and then differentiate it. Now, just this differentiation is actually give us the slope. And of course, it becomes maximum or minimum when the slope is 0. Yeah? And of course, the same idea like last time, we solve it through the tangent idea. Now, if we know that expression for normal stress, and then we can immediately identify how to calculate the maximum and the minimum principal stress, maybe we can do it here too. Okay, that sigma s, theta s is the orientation of the plane of the maximum and the minimum shear stress, of course. Okay, now if we have the expression for tangent, the same idea, we can use triangle to find it. Okay, since the concept is quite similar, I'm not going to explain in detail. It's the same. We know two sides of the triangle, then we can use Pythagoras, and of course we can work out what is the value of the sine and the cosine. Okay, with the idea of this is the whole 4 quadrants, then there must be the opposite quadrant we have to contend with, and that is of course this 2 sine to the 2 theta s2. The same idea, we can work out what is the sine and the cosine for that angle too. Once we got this set of the angle, then we go find one by one. We start off with the maximum in-plane shear stress, which is relating to theta s1. Okay, the same idea, using equation 2, substitute into it, then work it out, we find out the maximum shear stress. And then if we work out the normal stress on this plane, we use the angle of theta s1, then of course it means that we remain with the sine and cosine of 2 theta s1, substitute into equation 1 to find out the normal stress, substitute it, there we are, work it out, and then we have that x, sigma x plus sigma y over 2. Then move on to the minimum. Again, we will already work out the sine 2 theta S2 and the cosine 2 theta S2, and then we move on into using that equation, substitute into it. Then we have the minimum shear stress. Okay, and of course the last time the maximum is positive of that term, the minimum is negative, therefore we actually conclude into that form there. Okay, and with the two same theta, sine 2 theta and cosine 2 theta, we're going to work out what is the normal stresses as well. Of course, substitute as usual. Then work out should be still sigma x plus sigma y over 2, which means when we see the maximum shear stress, then we also see the minimum shear stress, and the normal stress in all components is sigma x plus sigma y over 2, and we have expression to find out those orientation as well from the tangent equation. Okay, I think we should summarize this stress transformation a little bit. That's okay. If we just rotate the element by theta anti-clockwise, then we have that equation to sort out the normal stress value and the shear stress value. Then we move on to find out what is the maximum and minimum normal stresses, which we call maximum and minimum principal stresses, and we work out the orientation, we work out the value, and we also find out that the shear on those planes are 0. We move on to find maximum shear stress. We have the orientation, we have the equation for the value of maximum and minimum shear stress, and of course the normal stresses is sigma x plus sigma y over 2. Sometimes we use the word sigma average. So that is what we have found so far. However, when we look at the calculation, we look at the equation, it's actually really complex. It's, well, you know, with the time when we don't have calculator at hand, this is really hard. So apparently they look at the form, these two, this equation and this equation, they said is a circle equation. I know you probably say, oh my God, at this moment, but once it becomes a circle, then we're going to refer it to Mohr circle. Okay? Well, before we go on, then this is the general equation for a circle. The center is at x naught and y naught. Okay? And of course, the capital R is the radius. We have equation here like that. We have equation 2. Oh, we just rearrange it first. Of course, we set up x as sigma x prime and tau x prime y prime as y. Okay. Then we square it up. We change equation 1 by square it up. Okay. Of course, that one is a plus b square. We then expand the term. Once we expand it, we leave it like this, and we call it equation 3. Then we go around and try to rearrange equation 2. This is our equation 2. Notice that there is no term that you move on to minus it. So it's like y not equal to 0 here. So we just square it up. Again, expand the term. And now if we bring up equation 3 to compare with it, okay, then notice there's a match here in the bracket. So we combine them. Okay. That the first term from equation 3 become the first term of the last equation. The first term of equation 2 here come down here. Okay. That and that combine. Notice that we have sine square plus cosine square. Then it become 1. If it become 1, then only the factor carry on. Okay. These two and these two the same. the same expression, minus plus disappear, 0. That one again, cosine square, sine square is become 1, then time the factor, we left with that term. So this is in fact, and don't forget, sigma x prime is variable, tau x prime y prime is variable. Okay, sigma x, sigma y constant, tau xy constant. The prime is the one that with variable. Therefore, it can be compared to the circular equation. Y naught is equal to 0, of course. Then, if we compare that way, if we plot a graph between sigma x prime and tau x prime y prime, then we should get a circle. Okay, the circle with the center at, of course, x naught and y naught, given here, sigma x plus sigma y over 2, and then 0. And of course, the radius is square root of that of the right hand side term of the equation. What does it mean? Here, right? The top one is our starting element. The bottom one is when we rotate by theta. Here, if we plot sigma and tau, right? The first plot will be this pair, sigma x and tau xy, the plot here. Okay. Second plot will be sigma y and tau xy minus tau xy there. If we draw a line, then notice, because we said these 2 points is on a circle, so if we draw a line connecting it, then we have the diameter line, okay, which means halfway it is the center of the circle. Don't forget that this one here and this one here, the difference is 90 degrees. And if in the physical sense it changed 1 theta, in the equation sense it changed 2 theta. So physical side 90, the mathematic is 180 degree. 180 degree means it's opposite side of the circle, right? Okay, so that become diameter line. And then of course we can find out using the coordinate, then we can find out that the radius is actually, as we said, the center is at sigma x plus sigma y over 2, 0. And if we look at the radius, then we form a triangle there. We know the size, right, by the coordinates. And therefore, the radius is there. Again, it is the same as the equation we find. Now, let's look at the principal stresses using the circle. Okay, so that is the sigma 1, 2, and then sigma 2, sigma 1, 0, and sigma 2, 0. Again, 0 mean the shear stress is 0 when it pairs with maximum and minimum principal stress, the same as our equation proof. And of course, the tangent, notice that it is again the same equation we proved from mathematics. Sigma 1 and sigma 2 will be using the coordinate. Okay, if we work out distance like so, and therefore, of course, from here to here is from center to a point on the circle. So the length is radius. From there to there, the same. Length is radius. Therefore, sigma 1, 2 is equal to that term, plus minus radius. And of course, when we put in the radius, then that one will be exactly the same as we proved from the equation. And of course, if we look at the maximum in plane shear stress, the same thing still happen here. Okay, the tan 2 theta s is working out again and proved to be the same as proved by equation. And of course, that height is radius, and therefore tau max, tau min is in that form, same as proven by equation. And of course, the first coordinate will belong to That's sigma x plus sigma y over 2, which means that is the normal stress when you find out the maximum and the minimum shear stress. Again, the same as calculation, the same as mathematically proof. And that, well, of course, is equal to radius itself. And as I indicate, the first coordinate, the normal stress, is as proved mathematically. Now, let's see example then. So, we're going to use Mohr circle to solve this. We want to find the principal stress and the orientation. We want to find maximum in plane shear stresses, and we want to find the stress, all the stress components when the orientation is 10, when we turn this element 10 degrees clockwise. Okay. There. Sorry. There. So basically, that is the beginning element on the left hand side. That is what we're going to do. We already use sigma x prime and tau x prime y prime. Okay. Now, that too, okay, if we turn it around, notice that that one is positive. The sigma x prime is positive, but tau opposite side negative. Okay. We turn that around, that is a positive sign, and apparently the shear this time is positive and the stress, however, opposite side negative. So we have our first two plots. Okay. A as we discussed, B as discussed. Again, I emphasize myself, these 2 points coming from physically 90 degrees apart, mathematically is always 2 theta. Therefore, mathematically, this is a mathematically plot. Therefore, this one here is opposite side of the circle, meaning it is a diameter line. Okay, and of course, halfway through is the center. Okay, then once we know the center, maybe we talk about the radius and the angle we are looking at. Okay, plot it down to the sigma, then we can work out the two sides. And of course, the radius is OA, or here, O here, A here, or OB, the same. Okay, but then we can calculate using Pythagoras, and then we can work out what is the radius. Okay, in general, once you work out radius, then notice that this is one thing that you have to be very careful about. This line here represents 0 theta on a physical plane. That line here is not 0 theta. That line here is 2 theta P1. Okay, so be really careful from the center onwards. Okay. So from the original line here, we turn here, then we get maximum principal stress. Therefore, that is actually 2 theta P1. Okay, and then we can work out using the side. Let's show the sides again. And then work out the value of tangent. Okay, we clear it off a little bit. Summarize what we have found here. Okay. Now, if you want to find the principal stresses, the best way is actually to draw the circle, because then we can see that the maximum normal stress is here. The minimum normal stress is here. Okay. Again, I emphasize that line from here to here is theta equal to 0 on the physical plane. That one here is theta equal to 2 p theta 1. Okay, that is sigma 1 0, and that is sigma 2 0. Okay, similar, the same. When we measure it that way, it still forms center of the circle to a point on the circle. It is equal to radius, and therefore we can work out sigma 1, and then we can work out sigma 2. Just general plus minus. Okay, And of course, theta P1 is half the alpha. Okay. Then the maximum shear stress, of course, the maximum is there. Oh, notice that the axis shear downward positive. Okay. There. What is tau max then? The radius, right? So, as we know, then the tau max equal to radius and of course equal to 23.05 megapascal. Okay, negative and positive the same, plus minus only. Okay. Then let's look at the stress orientation. We start off this picture. Okay. Then the question said they want to rotate the angle by 10 degrees clockwise. In this one here, then we have to train physical 1 theta, on the stress plane on the calculation 2 theta. So if physical you turn 10, here you turn 20, and then we have these lines. Okay, from there move to x, become x prime, y become y prime. Okay, let's call that point D. And of course we know the angle, and if we know the angle, then we can work out the height of the side and using sine cosine. Okay, like that. And of course then sigma x prime, which is the coordinate, then using the original point we measure at the center, minus 7.5 plus the length, in this case the radius times cosine 20.6. And of course we can work out sigma x prime. The height there is of course using sine of the angle, and of course tau x prime y prime is calculated using that expression. Notice that for tau it comes from 0, so we don't care about plus minus in front of it. Okay, and of course point E signify sigma y prime using the same idea. There we are, and then we have sigma y prime. Simple calculations. And then of course we could summarize the whole thing, adding in sigma 1, sigma 2, tau max, tau min. Okay, so that will be the complete picture of what we have done. And in summary, okay, we work out the principal stress and the orientations. We also work out the maximum in plane shear stress, and then we work out the stress orientation at 10 degrees clockwise, and that's it. And that is summary of the answers. Let's see what we have done today. First we discuss about the stress transformation. Okay, then we first talking about equations. We talk about rotating elements. Basically we look at the same point, the same set of stress, we just change the perception, look at the different angle. Okay, and the equations is proof for it. Then we find out that it's changing according to the angle we rotate. Therefore we find out the maximum and minimum normal stress, which we call principal stresses. We also find the maximum in plane shear stresses, of course with their orientation. We also said that rather than using hardcore substitution, we're going to use the graphical solution, the technique of Mohr circle. Okay, then we reduce the equation, the tough calculation, and then we understand the concept instead and change the idea into just using equation for circle and triangles. And that concludes the lesson on this topic. Thank you very much.